back to the simulation. So you use this button to expand, to make it large, and you use this button to start. So let's make it large and start. Notice we have circular motion going on, and it's constant speed, 20 meters per second. This is what it looks like if I increase the speed, and this is what it looks like at low speed. The radius, that's simply, I can make the circle bigger. Okay, big circle or little circle. And the mass. I can increase the mass of the object and decrease. Notice ones with acceleration and net force. We know net force is being pulled into the center, and for a larger mass, of course, we'll need more force to keep it in the circle. If I have a tighter circle, a smaller circle, I'm going to need more force to keep it in a smaller circle. Less force, notice here, less force is needed for a larger circle. Okay, not as much curve. And of course, if I want to go in a circle much, much faster, I'm going to need more force. So I'm going to have you look at how these things affect the force and the acceleration. Let's look at vectors. When you turn on velocity vector, you can see here the direction of the speed at any given moment. Velocity vector shows both speed and direction. We already know the speed, but notice the direction at any given moment. I'm going to pause it. See? It's like the people in a circle. If you are going to be moving, you're going to be stepping to your side at that moment. And the faster you are speeding, the bigger this velocity vector. What about acceleration? Well, recall that whenever we put a force on something, it's going to accelerate in that same direction. Newton's second law. Net forces cause accelerations, and they're always in the same direction. So here is the acceleration into the center as well, because that's where the force is pulling into the center. Always, always, always in the same direction as the force. And also note the shape. Wherever I am, my speed is to the side. We call that tangent to the circle. And acceleration is into the center. Okay, into the center always. And velocity to the side. And so on. That's the demonstration. Any questions on that? Okay. Cornelia, with me? I see your ceiling. Makai, you with me? I only see your ceiling. Can you angle your camera so we can see you? Okay. Thank you. Next up, let's go through the Canvas assignment. Okay, you'll find that in Module 6, Circular Motion Interactive. And this is the Canvas assignment. Open this PDF and either download it or keep the questions on screen, and we'll go through them now. So follow along with me, and we are going to go through it. Okay. Anna, this is in your email. Okay, I made a Word document so you can translate this text.
Okay.
Okay, so mira, mira esto es en inglés. Tú tienes su email,
Sí.
so you can translate. You can translate the text, okay, in Translate. Okay, so follow along. Thank you, Anna. So we already did this part here. We tried out the interactive, and we got familiar with it, and now we're going to use it. So move on to number 2. Velocity is a vector quantity which has both magnitude and direction. Use a complete sentence and describe the object's velocity. So focus on velocity and describe what is happening here. Don't forget to talk about speed and direction. Here's the speed. See how it gets the vector longer and shorter, and talk about the direction. Moving on. True or false? If an object moves in a circle at constant speed, the velocity vector will be constant. Okay, decide if that is true or false. When you look at this, decide if this vector is constant. And don't forget, vectors have speed and direction. So both must be constant if this vector is to be constant. Think about that. And then decide if this is true or false. Number 4. In the diagram, there are positions in the circle, and this is kind of like the do now and kind of like my story about people standing in a circle. Draw the velocity vectors at these positions. 1, 2, 3, 4, 5. Use the simulation to help you out to draw the direction at those positions, and also draw the acceleration. Draw the acceleration vector at these same positions. Okay, go ahead and use this button to turn on acceleration. Number 5. Describe the relationship between the direction of the velocity and the direction of the acceleration for a body moving in a circle at constant speed. Okay, so use your words and describe the relationship between this vector acceleration and this vector velocity. Number 6. Here's a question to think about. If an object is in uniform circular motion and then it is accelerating towards the center of the circle, yet the object never gets closer to the center of the circle, It maintains a circular path. It's always the same distance away from the circle. Why? Suggest a reason. Why is this true? Why are we always the same distance from the center? How can an object accelerate toward the center without ever getting any closer? Okay, put that into words. And finally, I think this is the last one. Nope. There's more, but here's more to think about. Suppose that we have position A, B, C, and D. And remember my story about people in a circle. If the person at A lets go, they will leave the circle at B prime. Okay, what do you have to draw an arrow in the diagram in the direction of the required force to get the person from B prime back to B? Do the same thing for C and D. And you will recall our discussion about the people in the circle. And then if the acceleration of the body is toward the center, what is the direction of the force? Newton's second law. Unbalanced forces make things accelerate, right? Use a complete sentence here and describe the direction of the net force. This is kind of to look and see what happens mathematically. Do these trials from A through F and just follow the directions here. Keep the speed constant, right? But change the radius. Tell me what happens to the acceleration. For part B, keep the radius constant and tell me when you move the speed up and down, what happens to the acceleration. Part C, if you double the speed, what happens to acceleration? Part D, if you triple the speed, what happens to the acceleration? Okay, you want to decide if it's 1 time, 2 times, 4 times, 9 times, 3 times. Okay, put in some numbers and test it out. See what happens. Number E is as the radius of the circle is doubled, so double the radius, what happens to the acceleration? Okay, less, more, 1/2, 2 times, 4 times, what happens? And do the same for when you take the radius and triple it. Triple the radius, what happens to the acceleration? You're going to see the relationship that happens. When you do A through F, you're going to see a pattern. Write a conclusion which you intelligently describe the characteristics, okay, how one thing affects the other. Give attention to speed, velocity, and acceleration. Okay, so what happens? Can you write a mathematical relationship between what happens to acceleration with speed? Right? Is it directly proportional, inversely proportional, squared? Right? Does it go as the square? And then talk about the let's see. That's pretty much it. I want you to look and see what happens to acceleration when you play around with the speed. They're missing here. There's missing a word. Give attention to quantities, speed, velocity, acceleration, net force, and radius. Okay, they're missing. That's another thing that we're playing around with is the radius. So there's one more word to add to your conclusion, radius. That's the end. Okay, the time is 9:31. Let's take a 3-minute break. And then we're going to work independently on that activity sheet. We can talk about questions before you start, and then we'll go to our breakout rooms. So 3-minute break. I'll see you back here at 9:35. 9:35. And stop recording.